Welcome to AP Statistics. Today, we are exploring one of the most important concepts in all of statistics, the normal distribution. By the end of this lesson, you will be able to describe the key characteristics of a normal distribution, use the empirical rule to estimate probabilities, and understand how to find areas under the normal curve. Topic 2.11. The normal distribution. We begin with the idea of a continuous random variable. Unlike discrete variables that you count, like the number of students in a room, a continuous random variable can take on any value within a range. Think of height, weight, or time. Because there are infinite possible values, we describe probabilities using intervals and the area under a curve. Many continuous random variables in the real world follow a specific pattern called the normal distribution. We often call this the normal curve or the bell curve. Notice its distinct features. It is unumodal, meaning it has one single peak. It is also perfectly symmetric. If you fold it at the center, both sides match. The center of this distribution is defined by the mean, represented by the Greek letter mu. The spread or width of the curve is determined by the standard deviation, sigma. The smaller the standard deviation, the more the data is concentrated near the mean, making the curve look tall and narrow. A larger standard deviation spreads the data out, resulting in a shorter, flatter curve. No matter the shape, the total area under any normal curve is always exactly 1, representing 100% of the probability. A very special case is the standard normal distribution. This is a normal distribution where the mean, mu, is exactly 0 and the standard deviation, sigma, is exactly 1. For any normal distribution, we use the empirical rule to quickly estimate probabilities. It's also known as the 68-95-99.7 rule. Approximately 68% of all observations fall within one standard deviation of the mean. This means if you know the mean and standard deviation of a dataset that is approximately normal, most of your data is right here in the middle. As we move further out, approximately 95% of observations fall within 2 standard deviations of the mean. And finally, almost all data, about 99.7%, falls within 3 standard deviations. If a value is beyond 3 standard deviations, it is considered very extreme or rare. Let's apply this to a real example to see how it works in practice. Suppose the heights of adult women in a certain city follow a normal distribution with a mean of 64 inches and a standard deviation of 2.5 inches. On the right, we have our normal curve labeled with 64 at the center and marks at intervals of the standard deviation. If we want to find the heights that represent the middle 95% of women, we look at the range within 2 standard deviations of the mean. Since one standard deviation is 2.5, 2 standard deviations is 5 inches. 64 minus 5 is 59. 64 plus 5 is 69. So, approximately 95% of women in this city are between 59 and 69 inches tall. What if we wanted the probability of a woman being between 64 and 66.5 inches? Since 64 is the mean, and 66.5 is one standard deviation above, and we know 68% is within one standard deviation on both sides, we just divide that by 2. There is about a 34% chance a randomly selected woman falls in this specific interval. When we work with normal distributions, we often use specific notation to describe the probability of a value falling in a certain range. If we write the probability that x is less than a, we are looking at the area under the curve to the left of that value. This represents the lowest percentiles. For example, if this area is 0.10, then a is the 10th percentile. If we write the probability that x is between a and b, we are looking at the area trapped between those 2 boundaries. This is the probability that a random variable falls within that specific interval. Finally, the probability that x is greater than b represents the area to the right. This tells us the proportion of values that are higher than a certain threshold. Remember, the total area is always 1, so the area to the right is simply 1 minus the area to the left. Sometimes we are interested in finding the most extreme values in a distribution, the outliers on both the high and low ends. To determine the most extreme p% of values, we split that percentage into 2 equal areas at the very ends of the curve. For example, if we want to find the boundaries for the most extreme 5% of data, we don't put all 5% on one side. Instead, we place 2.5% in the lower tail and 2.5% in the upper tail. This leaves the middle 95% of the distribution untouched. These boundary values, a and b, define what we consider unusual or extreme for that specific variable. You can find these exact values using a z-table or technology like a graphing calculator. We have now covered the fundamental properties of the normal distribution, the empirical rule, and how to interpret areas as probabilities. You are now ready to begin calculating specific z-scores and percentiles in your practice.